Using a limit to generate the integral is essentially the integral version of Newton's quotient. So what we can do is we can start with the discrete parts, these discrete rectangles, which is the sigma expression, and we can let n go to infinity, which means that we're going to use an infinite number of rectangles in that space, which is going to give us the exact area. So how can we interpret this expression as n goes to infinity of k equals 1 to n of this square root expression? How can we rewrite that as an integral? So the first thing we want to determine is expression for dx. And this expression for dx is always going to be the interval width divided by n. So if I take a look at this expression here, I want to work out my interval width. In this particular case, my interval width is going to be from 0 to 1. So this means that my interval width is equal to 1. And n can be a discrete number if we're going to use a discrete number of rectangles and do a Riemann sum. But in this case, we're going to let n go to infinity. So this is going to be a dx expression. Secondly, we want to determine the expression for x. Okay, so in this expression here, what is going to be the x part of this expression? Now, x is generally going to be based on the starting value, or left-hand edge, plus 1 dx for every k value. And that's going to give us right-hand Riemann sums. Now, if we want to have left-hand Riemann sums, we can let our k start instead of 1. We can let it start at 0, and that will give us left-hand Riemann sums. Okay, so left-hand Riemann sums could be, we could just change the k value to 0. That means that we're going to take the height on the left edge instead of our first height being measured at the right edge. Okay, so our example we're going to do are a right edge. So we're going to let our x be a plus I k over n. Well, our a value, we are starting at 0. Okay, and then our x then must be just I k over n. So what we want to do is look for I k over n. In this case, since I is 1, we're looking for expressions that are equivalent to, 1k over n, which we're going to use a limit to become infinite. And when we look into our expression here, we can see that our x value is going to be this portion here, which I've kind of highlighted in blue. Okay, so that's going to represent our x. We have a dx, which is our I over 1 over n in this expression. So we're going to start by putting that into our expression. So our f of x function is going to be the square root of 1 plus 3 k over n, which we're going to replace with x. And then we also have a 1 over n expression that we can replace with dx. So this is what our expression looks like so far. To work out the bounds then, we have to figure out what is our starting point and what is our ending point. For the starting point, we're just going to set n equal to infinity and k equal to 1 and plug that into our expression. So if we plug that into our x expression, so if we plug that into our x expression, so x, our a value is going to be equal to the limit as n goes to infinity of k equals 1. So we can let k equal to 1, and our n is going to go to infinity, so our a value is equal to 0. And that's exactly what we want here. So our a value is 0. The b value is going to be checked by working out the limit when n goes to infinity, and our k is also infinite. So that's going to be equal to, in this case, 1 because they're both linear expressions. So we can see that our bounds are going to be from 0 to 1. So now we have established our f of x expression with an x. We've found our dx expression, and we've also established our bounds, the starting point and ending point, by plugging in, working out the x value when k is 1 and the x value when k is infinite.